Okay, so my thesis is modeling neighborhoods as fuel for wildfire. I did this research for my Master's of Science in Forestry with the National Center for Landscape Fire Analysis at the University of Montana here. And modeling neighborhoods as fuel for wildfire in a nutshell is characterizing things like buildings that are known as the built environment by the features that make them flammable and likely to propagate fire in a computer simulation of wildfire. So I'm just going to start by introducing the problem space and kind of motivating this project. And after that, I'll get into my thesis, which was getting a lay of the land of the state of science and the gaps that exist currently. And how my research fills those gaps. My research was predicting structure susceptibility using a remote sensing method of characterizing features of the built environment as fuel for wildfire, and using a machine learning model to predict field assessments, and then using unsupervised learning to create structure archetypes with clusters of different homes. I'm also going to go over some practical findings that I found in the study area of Uray County, Colorado, and I'll wrap it up with some closing remarks. So to motivate the project, first of all, there are a lot of homes being lost to wildfire. Just 6 fires since 2018 are responsible for 38,000 homes being burned down in the US. And if you look on the left side of the chart here, a big cause of that is more houses being built into the wildlands, and wildlands are areas where fires are more likely to occur. So there's more houses exposed to wildfire, and the result of these homes burning down on the right side of the chart is enormous community impact, not just financial, but other externalities and insurance companies leaving homeowners and entire areas. And so how can we prevent homes from burning down in the future is the motivation for this project. So I just want to review risk because there's some key terms that I'm going to use in this presentation that I want to make sure we're on the same page with here. So when we're talking about risk, we're talking about a hazard. In this case, this is supposed to be a train track, and an asset that you want to protect from a hazard. In this case, it's the structure. So you can think of the train track as wildfire. So when you put an asset on the path of a hazard, that's called exposure. Now the home is exposed to being damaged or destroyed by this hazard. And you can manage exposure by diverting the hazard. In this case, we've just rerouted the train track. Or you can take the tracks away entirely before they reach the asset at risk. And the version of this, the way it applies to wildfire, is we have a before picture and an after picture here, upper left and lower right. And a way that you can take away the train track is by removing the fuel that makes wildfires big, so that the result is a forest that has less available fuel and is less likely to produce a highly intense wildfire should a fire occur there. Another way you can manage exposure is simply by stopping it by force. And the way that this is done is firefighting. And a lot of people in this room know that firefighting can only be done under certain conditions. It's very difficult to combat a natural hazard, and you can't just put a person in the way of a very intense wildfire that's coming towards a home. So a less talked about way of managing risk is managing the susceptibility of an asset. Susceptibility is the key term that my project is focusing on here. And when you manage susceptibility, you alter the asset itself. In this case, we've put a tunnel in the home so that anything except an extremely large train can pass through the home without actually damaging it. And the way that this applies to wildfire is through, and these are the last 2 terms I want you to remember, are through home hardening, which is retrofitting a home or building a home out of less flammable materials. Think like a asphalt shingled roof as compared to a wood shingled roof. And the second way is creating defensible space. Defensible space is defined by the National Fire Protection Association as the area within give or take 100 feet of a home, depending on the nature of the fuels and the surrounding topography. But to create defensible space, you're removing fuels so that there's less things to burn within 100 feet of the home. So should a fire reach a home, it's less likely to be intense enough to burn it down. And susceptibility is important to characterize for homes because homes do burn. This photo is courtesy of LA Times, and this is from the Palisades fire, and you can see all of these destroyed homes here. So currently, models are quite good at characterizing the hazard and exposure of fires in the wildlands, but they're not characterizing structures in good enough detail to say structure 1, 2, 3, 4, 5 have these features and therefore are this susceptible to homes. So I have objectives. I'm not going to go over all of them now because I'll address them one by one as we go through the presentation. But overall, the purpose of this thesis is to better characterize neighborhoods as fuel for wildfire so that those characteristics can be represented in these wildfire risk models that drive billions of dollars towards risk mitigation efforts in communities across the nation. So the first part of my thesis was the state of science and gap analysis. The objectives were to characterize the current state of research in this space and identify gaps in the research that inhibit progress in this field. And the way that this was done was doing a literature review of 118 studies, and this has been accepted for publication, not published quite yet. But one of the findings here is that there are a few different things, post-fire assessments, laboratory experiments, and statistical models in which people have gone to neighborhoods that were destroyed and looked structure by structure and said these were the things that led to this home burning down. And they've determined that these features are kind of classified into home hardening and defensible space. And those features, there are 12 main ones that kind of percolated up towards the top in the literature. The structure features are windows, roof material, vents, eaves, siding material, the architecture of the home, and the maintenance levels of the home. And the defensible space features that have appeared to matter are artificial fuels, so think like sheds, automobiles, wood piles, landscaping, which is like mulch or ornamental vegetation around your home. Adjacent homes can pose a threat to structures. Canopy cover is just the density of the vegetation around the home, and the topography, which is basically slope. So those are the features that describe structure loss empirically through laboratory experiments and post-fire assessments. We expected that we would see the features that describe structure loss also appear in models that predict structure loss. There are two types of models that seek to predict structure loss. The first is susceptibility indices. So I found 5 of these, and each one will take a number of features, and they'll look at a home and score it by each feature, and then the total score classifies the structure as low, medium, high risk of being lost. And what we found in these is that there's actually only one feature, roof material, that's common to all 5 indices, and a lot of the features among the rest of the models differ. And so the models aren't agreeing on which features should be used to determine the susceptibility of the structures. Additionally, where they do use common features, the features have different weights in the models. And the last part of this is that the susceptibility indices have to be conducted in person. So a person goes, looks at a structure, all of the features that they want to do, and then score the model, which makes scaling structure assessments difficult. The second way of predicting structure susceptibility is through these emerging WUI fire spread models. WUI stands for Wildland Urban Interface, and it's where the built environment either is adjacent to or intermingles with wildland vegetation. And these WUI fire spread models take the susceptibility of the home. So in this upper image here, the red square is kind of the target structure. And so they determine how likely is it, given a certain exposure to wildfire, that this structure will ignite. And then after it ignites, there are three mechanisms of fire spread. There's direct flame contact, which is the red circle, radiation, which is just radiative heat that can melt vinyl siding, for instance. And then there's ember transport, which is depicted in this black arc here. And so the structure, based on its features, will produce certain values of these different mechanisms of fire spread and propagate fire through a network of, on the lower figure here, it's structures, vegetation, and non-burnable surfaces. So you kind of have to think in WUI fire spread models differently about spreading fire. So again, we expected to see these features that have been linked to structure loss empirically appear in the WUI fire spread models, but they use the features to determine the likelihood of ignition and the nature of fire spread are actually the volume of the structure, just the size of it, and just the size of the vegetation. So with these, those appear to be the most important features. So the gaps in this chapter that we identified is that models disagree on features, and there's no standardized way of characterizing the susceptibility of individual structures. And so the recommendations that we put in this paper were to develop a method for collecting a feature set of these susceptibility assessments remotely, because the conceptual chart on the right shows that the number of structures that you can assess with in-person assessments is like minutes for a single structure, but when you get to thousands of structures is more like months or years. Whereas remote assessments, it might take days or weeks to assess a single or tens of structures, but it's a really similar time to do thousands or hundreds of thousands of structures. So with remote assessments, you can characterize a much broader area and help more communities. But there's currently no model for a susceptibility index for these remotely assessed features. And so another recommendation was to develop one of those models. And we suggested a feature set that can be assessed remotely. So this is a really similar table that I showed you earlier for the empirical features, except structure features does not have windows, vents, and eaves. Even though those are important, they're pretty difficult to measure with aerial imagery or LiDAR or something like that. So these were omitted from that, and the defensible space features are the same. And in this paper, we also detailed how to detect and measure the feature and what data sources you can use that are available publicly to characterize those features. So with that feature set and that gap analysis, the next step was to implement it and try to predict field assessments of structure susceptibility. And that was the objective. So this little county in the, it's the blue polygon in the southwest corner of Colorado. It's Ouray County. That was our study area. I'll go over all these data sources in detail, but I used 4 data sources. Microsoft building footprints. A building footprint is just a square that represents where a home is in bird's eye view. And LiDAR, I'll go over that. The Silvis Global WUI raster, and the Ouray County tax assessor was used to get data about structures. So through a number of feature transformations and intermediate steps, this column of blue parallelograms under feature set was the final feature set that was produced. And with this feature set, we trained and tested it on field risk assessments that were rapid wildfire risk assessments. I'll go over those in a second. And tried to see if we could use this remote feature set to predict those field assessments of structure susceptibility. So the rapid wildfire risk assessment collects 13 features of homes. What happens is a car drives by on the road and they stop at the driveway and they try to determine a little bit about the contextual fuels and topography of where the house is. They also have a few features on the bottom here about the driveway and the address that determine how easy it is for someone to evacuate or how easy it is for firefighting resources to access the home. They also collected some information on defensible space, including the slope right at the home. They collected a little information on the home hardening, and then finally the distance to a neighboring home. So the way that this was, each of those features is scored, and the final score produces a total overall rating of low, moderate, high, very high, and extreme. So these are the ratings that we were trying to predict in the model. And the way that I did this with the remote assessments was by characterizing defensible space with LiDAR, characterizing structure separation distance with Microsoft building footprints, characterizing the background fuels with the Silvis global WUI raster, and characterizing home hardening with tax assessor data from Uray County. So first is the defensible space. This was done using LiDAR. The LiDAR was obtained from the Colorado Hazard Mapping Portal. It is airborne laser scanning LiDAR. And the way that LiDAR works with airborne laser scanning is a plane flies over and it shoots a bunch of lasers down and it collects these points that have an X, Y, and Z value, and it produces what's called a point cloud, which is a three-dimensional model of points of the landscape and objects on it. So with that three-dimensional model, you can produce a two-dimensional raster, which is a grid that says what is the Z value, or you can, I'll talk about other metrics I use to, I derive from the point cloud into rasters. I created 4 rasters. Panel A here, all panels are showing the same spatial area. Panel A is canopy cover of vegetation or any object that's from 0 to 2 meters. And then within we're looking at red Microsoft building footprint and the purple defensible space buffer around each building. And so within the defensible space buffer, I got the average canopy cover at 0 to 2 meters in panel A. Panel B is 2 to 4 meters. Panel C is 4 to 8 meters, and panel D is 8 to 40 meters. And so this gave us an idea of the horizontal and the vertical continuity of fuels within the defensible space. The next was structure separation distance. So again, we have red Microsoft building footprints here, and they're shown over one of the LiDAR rasters. And I just used Python and the Shapely and GeoPandas libraries to determine what the nearest structure was and how close it was nearby. And in addition to structure separation distance, this is going to be a cluttered slide. I drew the defensible space boundaries around each structure and then counted how many adjacent structures are within the defensible space of the target structure. And that gives you an idea of the structure density in the area. So that was another feature. And then background fuels were characterized with the Silvis global WUI raster. This raster says, is this intermix WUI where structures and vegetation commingle? Is this interface WUI where there's the built environment that's right next to wildlands? Or is it non-WUI where it's just wildlands, which is this green area And structures can exist there, but they're so sparse that it's not actually considered the built environment. And then within each WUI type, they also have the type of vegetation, whether it's timber dominated or whether it's grassland dominated. And so this gave us an idea of background fuels. I took the centroid of each building, and the value of the raster at that centroid was what I used to characterize the background fuels. And finally, home hardening was characterized with tax assessor data. So from the Ouray County tax assessor, I got, my laser pointer stopped working. I got the sizes of the wood balcony, detached garage, the patio, the open porch, and then I'm skipping down here, but the square foot of the structure, the effective year built, which is the actual year built with maintenance and updates accounted for in the building, and the material of the exterior walls, and the material of the roof, the architecture of the roof, and those were the home hardening characteristics that I used. Then I fed them into a random forest model and tried to predict these rapid wildfire risk assessments. And what you're looking at here, the chart on the left, is feature importance in the random forest model. And the most important feature, interestingly, is the size of the property in acres. And this was interesting for a couple reasons. The rapid wildfire risk assessments, if they can't, so they just do a drive-by assessment, right? And if they can't see a structure, they just give it the highest risk rating. So it's going to be extreme risk if they couldn't see the structure. And properties on larger acres are presumably more difficult to see and therefore receive a higher risk rating. This is kind of interesting because it goes along with another study that did determine that most structures that burn down are actually not structures in dense neighborhoods. They're structures out in the wildlands, and properties that are larger are not going to be in dense neighborhoods. They're going to be more out in the wildlands. And so they're more likely to be lost, not necessarily because a bigger property makes you more susceptible, but that where bigger properties are located are more exposed to wildfire. And so it's possible that this rapid wildfire risk assessment is more indicative of exposure to wildfire than actual susceptibility. But the next most important features were all of the LiDAR features from the defensible space. And one more interesting thing is that in the rapid wildfire risk assessments, the roof was by far the most heavily weighted. If you have a wooden roof, you're almost certain to be of extreme risk. But wood roof is way down here in a very not important feature. And so there was some disagreement in what the tax assessor thought was a wooden roof and what the rapid wildfire risk assessments thought were a wooden roof. But here's the confusion matrix of, on the x-axis is what the model predicted, and on the y-axis is what the true label actually was. Most homes in the county were actually just the same risk rating. They were moderate. And so the model was trained on a lot of moderate structures, and it predicted a lot of moderate ratings. And so that's really what's driving the accuracy of the model. But I will point out that low and extreme did not get confused, and even low and very high did not get confused except this one in the model. So that's possibly a good thing, but those are the results of the model. The F1 score of overall accuracy was 67%, which is moderate to high. Sorry, I'm going to hide this. Yeah. So if we think about not trying to predict this field assessment, what else can we do with the remote features that we assess? The next step was to create structure archetypes. And the objective of this was to cluster homes by their features using unsupervised learning. to try to group them into different clusters that we can maybe say they have similar characteristics that make them more or less likely to be destroyed by wildfire. So with that whole feature set that I showed you, I reduced that to two principal components using T-stochastic neighbor embedding. And this enabled us to visualize and plot them in two-dimensional space. And when I did that, all these structure clusters kind of emerged, which you can see visually, but they needed to be labeled. And so I used density-based spatial clustering of applications with noise, otherwise known as DBSCAN, to label the points by how dense these clusters of points are. And then the dark blue are just considered noise. That's kind of an advantage of DBSCAN. If they're not close enough to a structure, it just gets labeled noise, and those weren't included in the analysis. So I'm going to go over what all these structures mean, because after all these clusters mean, because after labeling them, then I needed to organize and describe them. And when I did that, they came into this kind of taxonomic structure where there were two orders. Order one is large lot rural housing, and order two is small lot forested suburbs. And I should note here that this is using the data for the structures that we had rapid wildfire risk assessments for, and they didn't do any structure assessments in like a dense neighborhood. So these are all kind of rural housing. So the first structure archetype in large lot rural housing is dispersed shrubland housing. This is all grass and shrub area, and these structures are likely to have large balconies and patios. The next is shaded fuel breaks. These are just names that I gave them. And shaded fuel breaks are actually in wildlands. There's not enough structure density for it to actually be considered the built environment. But they're in timbered areas. There's a lot of vegetation coverage, especially in the defensible space, and they're likely to have a detached garage. Structure archetype 3 is prairie compounds. If you've driven through rural America, you've seen like these 1,000-acre properties with just a few houses in one corner of the property. That describes these. And I called structure archetype 4 large tinder boxes. So these are mansions that have wood roofs, wood exterior walls, wood balconies, and they're pretty new, and they're on very large properties. So getting into the second order, which was forested suburbs, smaller lots, these are mostly newer houses. Structure archetype 5 is newer builds in the timber suburbs. They generally have large porches, patios, balconies, and detached garages, but their home hardening is generally pretty good with no exterior walls or roofs. And private forest retreats is structure archetype 6. That's very similar to structure archetype 5, except almost all of these have wood siding. So the home hardening is different. And structure archetype 7 is riparian suburbs. These are homes that occur along creeks, and the way that this was classified is because in Uray County, the tallest trees are cottonwoods. And so this had high vegetation density in that 8 to 40 meter height class. And these are older homes with higher housing density. And the last structure archetype is complex roof types. So it might be difficult to see that on your screen, but the building in the upper right has a lot of peaks and valleys, and the valleys of roofs are more likely to collect embers, and collections of embers are more likely to start a fire. So these are the structures that could benefit the most from something like a roof-mounted exterior sprinkler system for home defensibility. So those were the archetypes that we defined. This was a proof of concept part of the project that is working towards creating fire behavior fuel models for the built environment. And something similar has been done for the wildlands. Scott and Bergen in 2005 published these 40 fire behavior fuel models that are used really commonly in wildfire simulations in the wildlands. And they created archetypes of fuels for timber and grasslands and slash, and there are 40 of them total. But in order to do this, they went out into the field, they observed these, they tested the fire behavior of each one of them in laboratory settings to determine what the heat output and characteristic fire behavior of each archetype is. And so in order to have this apply to the built environment, structure archetypes should be characterized more in a broader area, like across the nation or across the state or just in more counties. They need to be observed in person, and they need to be characterized through laboratory experimentation in terms of their likelihood of ignition and their fire behavior. So a lot of work needs to be done for that, but this is an important single step towards fire behavior fuel models for the built environment. So lastly, I want to go over some findings. If you take away all the supervised and unsupervised learning and the modeling, there is more utility to these remote assessments, and I'll just point out a couple of them. There are a lot that I found. But in Ouray County, in many counties across the nation, fire managers and community risk reduction programs will tell people, create defensible space. But in Ouray County, the majority of homes, more than 70% of them, have defensible space that actually extends outside of their property boundary. And so they don't have full control over it. And so for these homes, it's likely that home hardening may be of more value to reducing susceptibility than creating defensible space, unless you have the entire community involved in it. Another thing I did was isolated homes that don't have any adjacent structures in intersecting their defensible space. So you can see all of these homes that only have vegetation in their defensible space. And there were 165 of them that have more than 60% fuel cover in that defensible space. And so these are the homes that do have control over their defensible space and could really benefit from reducing it, because at least in the Lahaina fires in Hawaii, 60% fuel cover in defensible space was linked to 3 times more likely that a home would be lost to the wildfire. So in conclusion, my objectives were first to characterize the current state of research and identify gaps. I did that through the literature review. And then with those gaps, I tried to fill them by developing a method of remotely assessing structures and structure susceptibility using open data sources and a remote feature set. And with that, I predicted field risk ratings, which had moderate accuracy, and future research would do well to validate that with other models. And the biggest takeaway from this chapter for me was a need for developing a susceptibility index specifically for that remote feature set. And finally, demonstrate the feasibility of developing fire behavior fuel models for the built environment. That was done with unsupervised clustering of different structure archetypes, and was an important step towards actionable and replicable research, and hopefully a step towards creating fire fuel models for the built environment. And finally, all of this code for anybody on Zoom or here in person who's interested in validating or replicating this project, all of the code is currently on GitHub, but it's private. Over the next couple weeks, I'm gonna make a couple of clean versions, but I created a small Python package. There are tons of classes and functions that are in there specifically for like creating these defensible space boundaries and analyzing the rasters within them, cleaning data. All of that is in there. So if you're interested in following this research further and where it goes, you can. I currently have 0 followers, so please follow me on GitHub. No, I'm just kidding. And that's the end. I'll take any questions if anybody has any. Jacob.